You remember one of the first things that was mentioned in chapter 14 was that people at the time thought that you were blending, right? Like that was the way genetics was just this concept of blending. If you think about that, after you take blends and then you blend it again, you blend of a blend of a blend. Over the course of time, everything should just look identical. If you think about it, I think that it would. So obviously that's not the case, but incomplete dominance is almost a way or a method of a blending hypothesis. So whenever I think of incomplete dominance or I have to do an incomplete dominance problem, I think of blending. And let me show you how that works with an example real quick. Okay. So I'll talk about a system that is incompletely dominant. On the test or on the AP exam, your problem will always state if the allele or if the system is in a system that is incompletely dominant or completely dominant, or codominant or whatever it might be. So you kind of just always have to be paying close attention, but this is how you would do an incomplete dominance problem. I always think of a special type of flower called the snapdragon, which was mentioned in your book, chapter 14. And for snapdragons, the big R allele causes a red color. The little r allele causes a white color. So the dominant allele is red, the recessive allele is white. And the heterozygote, Mendel would have pictured as being red, but for snapdragons, it's pink. That's kind of why I said think blending above. Now we could run Mendel's experiment through this, or we could run these through Mendel's experiment, better put. So let's do that real quick. Remember in Mendel's experiment, you started out with two parents that were both true breeding, correct? So in the parental generation, we would start out with big R, and cross it with little r, correct? And that would result in the first generation, F1, they would all be what genotypically? Big R, little r, which would be phenotypically all pink. Right? Mendel would have said they would be red, but because it's incompletely dominant, we would go with pink. The F2 generation, do you remember how Mendel was able to get his F2 generation? Self-pollination of the F1 heterozygotes. So if we do a little Punnett square off to the side, with that generation, big R, little r, big R, little r, there's the production, right? And that comes out to be a genotypic ratio that is 1:1. That's 1 homozygous dominant, 2 heterozygous, and 1 homozygous recessive. And phenotypically, though, this would be a 1:2:1, and not a 3:1 as Mendel might predict. 1 would be red, 2 were pink, and 1 was white. Good? So there's an incomplete dominant problem. You know you would do this style of a problem if it said in the problem it's an incomplete dominance. Or it might say complete dominance, in which case you would be doing a Mendel problem. Good? That's not the only degree of dominance that we can talk about. There's one more style. We really don't ever do problems with it. It's something I've never seen on the AP exam. You don't really do a lot of problems with it at all, to be honest with you. It's a style called codominance. M versus N. M, N, or M, N. Yes. This is when you have two dominant alleles. They can affect the phenotype in separate
What do they do in there?
and distinguishable ways. Good? Okay. One last thing to mention right through this area is that a lot of times we view the recessive as being problematic, and a lot of problems that you have done, or even the ones that you have seen, and this is a true case, honestly, a lot of things that are recessive are problematic. Correct? You know, having little t, being the homozygous recessive gives you the problem that you experience, right? Some good examples of that would be sickle cell. Or, here's one I want you to know from this chapter. Tay-Sachs. Let's actually go over both of those real quick. What do we know about sickle cell anemia? Okay, so, red blood cell. Red blood cell shape is poor. That's because you have a bad gene for what protein? Very good. Hemoglobin protein. Is poor. It's actually mutated. It's messed up. Individuals that have big T are okay. Big T heterozygotes are okay, but they're carriers. Little t, they have sickle cell. They have the problem. Right? Or Tay-Sachs. This is a different disease. You might not have heard of this. This is a case in which the individuals are guaranteed to pass away. And they'll die actually in infancy. And the reason for this is because there is a protein that's messed up. There's a non-functional enzyme. And what this non-functional enzyme does is it causes lipid accumulation in the brain. Dominant. Or being a big T, or being a big T is a bad thing. It just happens that the homozygous recessive is the individual that survives. So it depends on which specific disease you're discussing. Like dwarfism, right? Dwarfism. That is an autosomal dominant problem. If someone is born with big T, little t, they're going to be dwarfs. They're going to be small. Cool? So I think we see that difference. So I want this to get out of your head that little t is sad face. It could be happy face. Like, as far as, like, dwarfism is concerned, that gene, like, you all are little t. So, and that's obviously, like, therefore you are the height that you are. Good? Okay. Let's move on.